I'll say in a sec. Let me just begin with a word of prayer. No. Dear Father, we thank you for this day again, Lord. I thank you for these students. I just pray that you'd guide our work today, Lord. In your name I pray. Amen. Yes, this is the quiz you just took. I don't know. I guess I can work it out. So this suggests that yp has the form at squared plus bt plus c plus d. Oh, no need. So yp prime is 2at plus b, and yp prime prime is 2a. So let's see here. Yp prime prime plus 3yp prime plus 2yp is equal to t plus 2. That gives me 2a plus 3 times 2at plus b plus twice at squared plus bt plus c equals to t plus 2. So this gives me 2a plus 3b plus 2c equals to 2 from the constant coefficient. From the t coefficient, I get 6a plus 2b equals to 1. From the t squared coefficient, I get 2a equals to 0. So the smart way to solve the system of equations is in reverse, right? So I'll solve them like this. I'll start with the last one. The last shall be first. A equals to 0. Okay. Once I know that a is equal to 0, that tells me b is equal to a half. From the middle equation. Once I know that b is a half and a is 0, I get, I'll write it down, 3 halves. 3 halves plus 2c equals to 2, because a is 0. Why is there a fly in here? Let's see here. Looks like 2c is equal to a half. So therefore, c is equal to 1/4. Ah! Let's see here. And then, so y is equal to, oh, pesky homogeneous solution. I forgot to do it, right? Sorry, my work is rather awful here. So you should take points off for formatting for sure. Let's see here. 3 lambda plus 2, lambda plus 1, lambda plus 2. So you can see that the characteristic values, -1 and minus 2. So therefore, y is equal to c1 e to the minus t plus c2 e to the minus 2t. A was 0, b was a half, so plus t over 2. Plus 1/4, yeah? Yay. I see celebration. This is good. Yes?
So, for yp, I didn't do t squared. I just did 2at plus b, and I still got the same answer. Do we have to do t squared?
No, we do not. Why on earth did I do that? So this illustrates an important principle. You can always write down a more general answer, which includes the correct minimal answer as a subset, and you won't be wrong, but you won't be right. Like the not so right thing about it is that I had 3 equations and 3 unknowns when I could just as well have had 2 and made my life easier, right? This is sad. This is very sad what I just did. You know, if I saw this on a test, I would assume I hadn't studied. This is very bad. I'm so sorry. This definitely should not have been in our calculation. Man, embarrassing. All right, number 2. So my apologies for that. Number 2, we're looking at d squared plus 1 acting on y, right, equal to cosine of t plus e to the t. This warrants an annihilator of d squared plus 1 times d minus 1 to annihilate that. And so this gives us d squared plus 1, annihilate it. We get d squared plus 1 squared times d minus 1 acting on y equal to 0, which of course has general solution. Y is equal to c1 cosine t plus c2 sine t plus c3 t cosine t plus C4 t sine t plus C5 e to the t. These two pieces are the homogeneous solution, and so this is my generic form for yp. Just to clean it up, the answer that you should have suggested is yp is something like at cosine t plus bt sine t, and then plus c e to the t. Now, if you were trying to find the values of a, b, and c on your quiz, you do not know how to follow instructions. See what I said here? But do not find a, b, c, etc. So what I'm saying is stop there. Is good? All right. I should have obviously made this a 10-minute quiz. My apologies. But anyway, no one's complaining. All right, so superposition, complexification, and whatever else I get to. But the ever else I get to, I'm hoping to get to the Cauchy Euler problem and to explain to you maybe variation of parameters in a slightly less standard context. So let's start with the superposition principle. If we have L, all right, is, say it's a mapping from, say, functions on the reals to functions on the reals. So, and you know what, we could, let's be greedier. Let's say smooth functions. Smooth functions. So L, what is this? Basically L of a smooth function, what is it? Another smooth function, right? Not the same one, but a new, usually, smooth function. This is an operator. It's a linear operator if what? We have L of C1 y1 plus C2 y2 equals to C1 L of y1 plus C2 L of y2, right? This makes L a linear operator. So we've talked about these in some depth in here, right? Now, we can also talk about the complexification of a linear operator. So how do we, what do we mean by complexification? Complexification of L. What's that look like? So that would be, we do something like L of y, y1 plus I times y2, all right? Basically, we extend the operation of L to complex functions. And the way we do it, it's very boring. We just assume that it works out like this. L of y1 plus I times L of y2. We've actually already done this, believe it or not. I mean, the derivation I did for the homogeneous problem, I said, oh, well, we can, you know, we can do the same calculus for complex functions, so we can let lambda be complex, right? If you really look at that, what I was doing was I was extending the differentiation operator and the square of the differentiation operator, the cube of the differentiation operator, polynomials in the differentiation operator, right? And I was saying when it acts on a complex function, the way it works is you do the operator acting on the real part plus I times the operator acting on the imaginary part. I mean, that is the calculus that we did. And what that is, formally, is complexifying the operator. So the central theorem that we used was what for that? If we have L of y1 plus I, excuse me, y2 equals to 0, then L of y1 equals to 0 and L of y2 equals to 0, right? So we used this complexification trick to get two real solutions from every complex solution, right? We did this. Yeah? Now that was for the homogeneous problem. So now I want to kind of level up here and try to take another look at what does complexification do for us for non-homogeneous problems. And this is very much tied to the the principle of superposition. Maybe I should just talk about superposition on its lonesome and then talk about this, but it's too late. So what's the principle of superposition? So what I'm after is trying to give a corresponding theorem for non-homogeneous problems. In fact, I already showed you an example of this idea at the very end of last class. So I kind of put the cart before the horse there a little bit, but superposition says the following. Superposition theorem, all right, for L linear smooth linear operator. And so what I mean by that is that it takes in a smooth function and it outputs a smooth function, and it's also linear, all right, a smooth linear operator on C infinity R. If L of, let's say, yp1 is equal to g1, and L of yp2 is equal to g2, right? Then L of c1 yp1 plus c2 yp2 is equal to what? What's that? Yeah, c1 g1 plus c2 g2. The proof of this theorem is like a line, right? I mean, how do you prove this theorem? I don't do too many proofs in here, but here it is. It's a linear operator, right? So that's C1 L of yp1 plus C2 L of yp2, right? But what did we assume that P1 and P2 were, yp1 and yp2? They are particular solutions, right, that give us back G1 and G2 respective. So this is just C1 G1 plus C2 G2. And there you go, and a proof. This is the kind of proof I expect you to be able to do in here. Seem fair? I think so. I hope so. If you disagree, get out. Change your major. No, wait, it's too late. It's too late. It's too late for that. So here, example 1. So here's an example. We could be looking at, so something like my prime prime plus k times y equals to force external 1. And we could look at my prime prime plus ky equals to force external 2, right? Where the external force 1 and the external force 2 are two given functions, all right? So we do the math we've learned how to do. You guys just did on the quiz. And so for this, we would solve, right? And you could obtain, myp1 prime prime plus kyp1 equal to f external 1, right? And we could solve the second problem. And we could find a second particular solution for that second external force, the same homogeneous piece, right? And if we did that, if we solve that, find this yp1, find this yp2, then superposition says that if we solve the problem my prime prime plus ky equal to f external 1 plus f external 2 has particular solution, which is just the sum of yp1 and yp2 as a special case. So so what this says is that we're looking at this like spring mass problem, right? And if we put one external force on it, we get one response, yp1. If we put a different external force on it, we get a different response, yp2. If we put the sum of both forces on this spring mass system, then the net response is just the sum of the responses one in each. This is the method of superposition. It says that the net effect is the sum of the individual causes. This is kind of a signature of a linear system, is that we can understand the big picture, the big result, as a sum of little results, right? In contrast, a nonlinear system has some kind of feedback, where you can't just understand the outcome as a sum of the parts. It's got some kind of self-referential cycle in it. These kinds of problems are harder to solve. But important, right? So, here, let me be less vague. Example 2. Let's see, you guys solved for me last time. Y prime prime equals to cosine t has what solution? What is it? Is it 1/2 cosine t? 1/2 t cosine t, is that right? Is right? I can't remember what we worked out. Suppose I'm right. On the other hand, if I wanted to solve y prime prime plus y equals to t, what would I use? T. I can do that one in my head. Let's see here. What if we had, you guys work this out with variation parameters, y prime plus y equals to, did we do this one, secant of t? I think that was my first example of variation parameters. On the quiz, I gave you tangent 2t because I'm evil. Yp3, I think, actually just works out to the natural log of the, what is it? It's like cosine t natural log the absolute value of cosine t secant. I forget what this stupid one is. Tell me. ln of cosine t, is that it? Okay. It's funny, the other two pieces cancel out. Like there's, in principle, you got y1 v1 plus y2 v2, right? But there's a piece of the y2 v2 and the y1 v1 which just cancel and just leave us this log term in that calculation. So anyway, all of this said, if I was to solve y prime prime plus y equal to, say, minus cosine t plus 3 times t plus 10 secant t, I can solve this corresponding problem without further calculation by the method of superposition, is my point, all right? So this has particular solution, you know, minus 1/2 t cosine t plus 3t plus 10 times the cosine of t natural log the absolute value of cosine t by the method of superposition, right? All 4 of the differential equations I just wrote down have what? They have the same homogeneous solution, right? That's not the general solution. That's just a particular solution. What would the general solution be? Right. Okay, so this is superposition in a nutshell. But superposition also works for the complexification. This is the sneaky thing. We can also use the superposition idea in complexified problems. Let me show you how it works. I mean, this is, I don't know, is this exactly, I'm not sure this is actually superposition just yet, but let's talk about complexification. There's some sort of like mixture of these ideas that you can use. So if I'm going to solve, say, y prime prime plus 3y prime equals to, say, sine of t, right? A game I can play is to say, well, instead of this, I'm going to, so this is equal to the imaginary part of e to the it, right? And so the idea is that I will instead trade for let's say, z prime prime plus 3z prime equal to e to the it. That's actually what I've actually done, technically speaking, is I've complexified the problem. I'm not really, I've traded, here I had L, which was d squared plus 3d, and it was acting on the smooth functions, right? Here I have my operator, you might call it L hat or something. It's still d squared plus 3d, but now it's acting on these things. It's like working on the sum of the smooth functions and I times, so it's working on smooth functions plus I times smooth functions again, right? Complex valued functions, if you like, to give a less weird description of it. It's working on smooth functions from the reals that have outputs in the complex numbers, right? Like e to the it is something like that. And so I can solve this in a very natural way. I just say zp is equal to e to the it, right? So zp prime is I e to the it, zp prime prime minus I squared, right? E to the it, which is otherwise known as minus e to the it. So this makes the calculation very easy because I've got zp prime prime plus zp prime, right? That's supposed to be equal to e to the it. And that actually is what? It's minus e to the it plus 3i e to the it equal to e to the it. And I think I have forgotten a very important thing. Man, I tell you what, maybe I should just call it a day. Sympathetic. Sad, 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 sad. What am I missing? A, right. A. There we go. I've now funsified the example. Sorry. That's funny to me. So that's actually a times 3i minus 1 equals to 1, right? Now this a, it's a complex calculation. We expect a complex constant, all right? So that's the cost of the method. You have to do some complex arithmetic. This tells us that a is 1 over, 3i minus 1. What you want to do there is you want to put that in Cartesian form. How do you put 1 over 3i minus 1 into the Cartesian form? Multiply by the conjugate over the conjugate, right? It's the complex analog of like rationalizing a root or something. So this is, we do minus 3i minus 1 divided by minus 3i minus 1. So I get minus 1 minus 3i upstairs, and downstairs I have 10. So consequently, z equals to minus 1 minus 3i divided by 10 e to the it. This is my particular solution, right? Now I know from my theorem, right? Well, okay, so this is the thing. I have this theorem for the homogeneous case. What's the corresponding theorem for complexification? What's the theorem for what's the non-homogeneous complexification theorem? Let me write it over here to keep it so you can contrast them side by side, right? If you have L of y1 plus I y2, right? If that's equal to, let's say, that's equal to G1 plus I G2, all right, then L of Y1 equals to G1 and L of Y2 is equal to G2. This is the sort of non-homogeneous version of this, which is what we use in the method of phasors in electrical engineering. This is what's behind using the method of phasors to solve sinusoidal problems. Instead of looking at cosine, we look at e to the it in that idea. Okay, so that's the theorem that we're going to use. So I just have, so for me, this is my ZP, you know, and this at the moment is the e to the it, right? E to the it is what? E to the it is cosine t plus I sine t, right? So on the other hand, ZP is minus 1 minus 3i divided by 10 times cosine t plus I sine t, yeah? Which is what? So 1/10 of minus cosine t plus sine t, because my I squared is minus 1, but there's a minus 1 already present. And then I've got plus I times 1/10 of minus 3 cosine t minus sine t. All right. What is it? Where did my 3 go on the sine is a very, very good question. Still in the marker. Let's see here. There we go. Much appreciated. So just to connect with the theorem I wrote on the left board, I'm thinking of this as being the G1 in the theorem. This is the G2 in the theorem, right? So I have this, you know, this result. I have that L of, oh, I'm sorry, I'm an idiot. Is that, no, that's not G1 and G2. No, I'm an idiot. This is not G1. G1 and G2, that's these guys. This is G1, this is G2, right? The language. So the ZP, these would be the what I called Y1 and Y2 in the theorem. Right? This would be the Y1 in my theorem. This would be the Y2 in the theorem by identification, right? So what I have is I've got that L of Y1 plus IY2 is equal to G1 plus IG2 with those appropriate identifications, which says to me that L of Y1 is equal to G1 and L of Y2 is equal to G2, which tells me that Y prime prime plus 3y prime equal to cosine t has y equals to, has a particular solution yp of 1/10 minus cosine t plus 3 sine t. And also, this one tells me y prime prime plus 3y prime equal to sine t has a solution yp equal to 1/10 minus 3 cosine t minus sine t. So I solve both the sine problem and the corresponding cosine problem at the same time by just finding a particular complex exponential, a particular solution built from an imaginary exponential with a complex coefficient. This is a calculational technique that we can use that is very simplifying for pure sinusoidal problems. Like if the forcing function happens to just be a pure sine or cosine, this is a pretty good calculational method. And it's the basis of what you guys call the method of phasors in electrical engineering, which I would love to make more explicit, but as I said, my hour of preparation for class was robbed by an inane scheduling meeting. Yes?
So that's the answer for the problem that you gave us is the second one?
Right. This would be the answer for the stated question. Yeah.
And then we don't have to go through all of this if we don't want to find, like, yes or no, right?
Oh,
We have to go through all of this.
you do not have to do this if you don't want to. I'm sharing with you yet another technique to solve a problem you already know how to solve. In fact, this is our third method. You could solve this with just particular solution, undetermined coefficients, right? And that's probably how I would do it most of the time. This would be the dumb way to do it. You could solve it with variation parameters. Don't do that. That would be dumb. Or you could use this imaginary technique. But the real reason I'm showing this is to try to demystify the phasor technique for those of you who are electrical engineers. I want to give you a little bit more mathematics in that direction, so when your engineering professor just does it, maybe you can connect the actual math to what they're doing, ideally. When you guys study phasors in electrical engineering, you should definitely take a look at the Wikipedia article on phasors. It's really good. It's got a lot of detail and some pictures which are really helpful to understand what's going on. All right, enough about that. So this is, I try to ask a question about superposition on the test. I do want you guys to know what complexification is because it's such an important idea. So there's that. With the time that remains, I'd like to talk about the Cauchy Euler problem. Okay? So we've talked about some general theorems for differential equations, linear differential equations. And these, I've stated some theorems that apply for as long as the coefficient functions to the differential equation, they don't have to be constants in the theory. And this is the one of the examples I could give for you that is an example of something like that. So here I'll state the general one. It's something like this: x to the n, d to the n, plus, let's say, a n minus 1, x to the n minus 1, differentiate n minus 1 times, plus plus a sub 1d plus a sub naught. All of this acting on y equals to 0. This is the nth order homogeneous Cauchy Euler problem. Now, in my notes, I explain an operator technique, all right? In fact, if I call this thing, L, so in other words, I'm saying that this whole thing is L. I mean, this is a theorem, is that L is actually equal to some polynomial in the xd operator. So we can write L as something like xd minus lambda 1, to the m1 power, and then things like xd minus alpha 1 squared plus beta 1 squared to the n1 power, and so forth and so on. You can actually factor it into a product of xd minus lambda 1 and all the way on out to xd minus alpha 1 squared plus beta 1 squared, like so. And then you could build up a series of lemmas just like we did, which would show you the solution set to each one of these operators, and then you just take the list, you take all of those and string them together, and that's your solution set. In other words, everything we did in terms of operator factorization for the constant coefficient case can also be done for the Cauchy Euler case. You won't find this in books. I'm not going to take that approach because I think there's an easier way for us to go forward today, but I just wanted to let you know that what we did could be done for this Cauchy Euler problem. All right? It could be done. We won't take this approach, though. What I'm going to do is take a really, really different approach, which is just to guess. Let's guess that the particular solution, oh, I'm sorry, not particular, let's guess that our solution has the form x to the r. Now let's just plug it in and see where it takes us. What happens when you differentiate? What's the derivative of y? It's rx to the r minus 1, right? So xd acting on y gives us what? It gives us x, r, x to the r minus 1 just gives us what again? Looks like it gives us x, rx to the r, right? Which is, of course, r times y. What happens when we look at differentiating 2 times? What's d squared acting on this y? Right? R times r minus 1, x to the r minus, oh, I'm sorry, minus 1? No, 2, thank you. Estos. So, x squared d squared acting on y equals 2. Looks like r squared x to the r, right? Also known as r squared times y. Starting to see a pattern, maybe? You continue down this path, it's fairly easy to see. You math majors, you can prove this by induction. X to the n, d to the n, acting on y gives us what? Yep, r to the n, r to the n y. So, and you put this all together. If you take the polynomial in the xd operator, excuse me, if you take L rather, let's look at L. L acting on y, L acting on x to the r gives me what? If I say it's kind of complicated, right? It's kind of complicated what that does. I mean, it gives us r times r minus 1 times r minus 2 dot 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 dot. I don't know how many r minus n. If we what is? Oh, I'm sorry. You guys, you shouldn't have believed me there. That's nonsense. Come on, guys. You guys, I'll let you fish. You got fished in. No. Come on. Look. This is what I get for skipping a step. R times r minus 1. Right? We get r times r minus 1 x to the r. So that's r times r minus 1 y. It's much worse than just r to the n. It's r times r minus 1 times r minus 2, and so forth and so on until we get r minus, if we're 2, we all go to subtract to 1. If we're going to the nth, we go to subtract n minus 1. That's what we have here. Ha, I tricked you guys. Let's see here. Okay, that was not on purpose. So that's just from what? That's just from the leading coefficient. Then plus an minus 1 r times r minus 1 times r minus n minus 2 plus, I'm going to go all the way to the end, plus a1r plus a naught, this whole monstrosity times x to the r equals to 0. So all I'm doing is I'm pointing out if you plug x to the r into this equation, each one of these terms gives you back a constant times x to the r. This gives you back r x to the r. The next one gives you r times r minus 1 x to the r. Every single term in here returns x to the r. Because you differentiate, if you differentiate, basically we're differentiating, let's say, k times, but then we're multiplying by x to the k. So we reduce the power by k, but then we increase it by k by multiplying back by x to the k. So every single term results in x to the r times some constant. Those constants are somewhat complicated, but here they are. Right? So in order for x to the r actually to be a solution to this differential equation, what do we need? Need r times r minus 1 dot 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 r minus n minus 1 plus a sub n minus 1 r minus 1 dot 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 r minus n minus 2 plus dot 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 plus, let's say, a2 r times r minus 1 plus a1 r plus a naught equals to 0. So this is the characteristic equation for the nth order Cauchy Euler problem. I forgot a very important thing at the start of this discussion. I should choose n equals to 2. I actually tend to test you guys mostly on n equals 2. What does this look like in just the n equals 2 case? It's much easier to think about, right? So we would be facing x squared y prime prime plus, let's say, ax y prime plus b plus by equals to 0. This is the n equals 2 Cauchy Euler problem. So if you set y equals to x to the r, then from this we get r times r minus 1 x to the r plus a times r x to the r plus b x to the r, which is r times r minus 1 plus ar plus b, parentheses, x to the r equals to 0. So in order for x to r to be the solution, what do we need? So there you go. This is the characteristic equation for the n equals 2 Cauchy Euler problem. I can solve that. It's a quadratic equation in R, right? And those two solutions will give us the homogeneous solution set, the fundamental solution set to the Cauchy Euler problem. In the same token, the nth order problem is an nth order polynomial in R. Fundamental theorem of algebra says that there exist n distinct solutions, possibly repeated, possibly complex. And guess what? Those n distinct solutions to the polynomial equation will produce n linearly independent solutions to the Cauchy Euler problem, provided we know about the complexification technique. And we also have to deal with repeated roots. What happens there? It's not quite the same story anymore. Let me be explicit. Let's solve some of these, right? The problem of factoring the operator, I deal with in the notes, and I do a fair amount in my notes on that. And it basically goes back to one of the first examples I did for you guys in operators, where I showed you that xd squared is not equal to x squared d squared. So this is what wrinkles. I mean, that's essentially why we have this way more complicated characteristic equation. It's exactly that. That's what causes the characteristic equation not to just be the simple thing, you know, r squared plus ar plus b. That actually is kind of the reason behind it in some sense. But again, I'm trying not to talk about this, so let me stop talking about it. Example 1. How about this? X squared y prime prime plus y equals to 0. Okay, so let's write down the characteristic equation, which in this case is, we guess, y equals x to the r. See where that takes us. It gives us r times r minus 1 plus 1 equals to 0. Did I say, fine. I think I chose poorly, guys. This is r squared minus r plus 1 equals to 0. And yeah, fine, I'll take my medicine. This is r minus 1/2 quantity squared, right? Plus what? I heard a 3/4. Yeah. So this is a complex case, actually. R is equal to 1/2 plus or minus I times the square root of 3 over 2. What do we mean by x to the r when r is complex? If r is equal to alpha plus I beta, then what on earth is x to the r anyway? I put down some internal student dialogue there. Let's see here. So x to the r, this would be x to the alpha plus I beta. How can we make sense? So first of all, if there's any justice, that should, come on, that's got to be x to the alpha times x to the I beta, right? I mean, that's got to be what that means, for one thing. X to the alpha, alpha being real, that's nothing controversial there. We talk about real powers of x, no problem. X to the I beta, though, here's the trick. We should think of this as follows. This is going to be e to the, let's say, log of x to the I beta. And so what that is x to the alpha e to the I, let's say I natural log of x. Here, sorry, natural log, right? We use natural log in here. So that should be e to the, oh, I'm sorry, what happened to my beta? That should pull out too, right? Supposing that properties of logs extend to imaginary domain. And so, man, this is just a heuristic derivation for you guys. So what I'm about to write, we'll just take as the definition, all right? So here you go. Here's a definition for you. X to the alpha plus I beta is defined to be, for this class, this right here. And I said it's a definition, but I just kind of gave you a plausibility argument right above there. That's why this is a plausible definition. And this is, of course, for positive x. In fact, this differential equation has trouble at 0. At 0, this differential equation doesn't really make sense. So the domain of definition for this differential equation is either x positive or x negative, but we can't have 0. So what we get is x to the 1/2 plus I root 3 over 2. Well, that's equal to the square root of x, which is x to the 1/2, you know. Square root of x times what? Times the cosine of root 3 over 2, natural log of x, plus I times the sine of the square root of 3 over 2, natural log of x. And then, am I looking for a complex solution to this problem? No. I want a real solution, right? So what do? I use the complexification technique to peel off the real and imaginary parts of this as my real solution. So from this, I see that y equals to c1 square root of x cosine of the square root of 3 over 2 natural log of x plus c2 square root of x sine of the square root of 3 over 2 natural log of x. That, folks, is the general solution to this Cauchy Euler problem. I seem to have led with the most confusing case. Sorry about that. How can I make this less confusing? Like, just stop. I mean, I should stop giving you guys ideas. Okay, so example 2, how about if we stick a prime? Check it out. X squared y prime prime minus, plus y prime equals to 0. The addition of that prime makes this problem way different. See, because then we have characteristic equation r times r minus 1 plus r equals to 0. Oh my goodness, I have the worst luck today. And so that is r squared equals to 0, right? So apparently I have a repeated root case. So I led with the complex root case, tried to make it easier. Now I'm to the repeated root case. Good job, right? So one of these, so y equals x to the 0, that's easy enough. So one of the solutions here, like y1, the constant solution 1 is, I mean, and that's pretty obvious when you look back at the differential equation that that is a solution, right? Constant solves this. In retrospect, you're like, well, I didn't need all this theory you've been telling me about. I knew a constant solution to this just from looking at it, right? What about the repeat? See, because the theory of differential equations still holds. Second order problem, the fundamental solution set should have 2 linearly independent solutions. This is one, right? Where's my other one? So here's something I don't know if we thought about this much, but before we had e to the lambda, like say e to the lambda x, right? If you partial differentiate that with respect to lambda, what does it give you? You're like, I don't know, that's weird. I don't usually think about partial differentiating with respect to the characteristic variable, you weirdo. But if you do that, that gives you x e to the lambda x. Ooh, that is the repeated lambda case, right? So if it works for that, why don't we try it out here? What would be partial r of x to the r? You're like, r times x to the r minus 1. No! That's a different differentiation. Now we're differentiating with respect to the exponent. This is an exponential function with respect to r. The base is fixed at x. So we have log x, x to the r. And in fact, that's correct. This is the second solution. So y2, natural log of x times x to the 0. In other words, just log x. Y c1 plus c2 log x. There you go. Of course, this is for x greater than 0. That's the general solution to this problem. Now, I haven't proved to you that this is actually a solution to that problem, right? This is a heuristic argument I've given you at the moment. I should probably spend 10 minutes to try to explain to you why both of these calculations actually make sense. I'm not going to try to do that today because, well, we don't have 10 minutes. But this is, in fact, the general solution. By the way, what would be the solution for negative x? So there you go. That's the negative x solution. Just replace your x with absolute value of x. The last problem, if I want to give you the solution for negative x, there's for x less than 0. Yeah. You just wrap all your x's in absolute value. That'll be the negative x solution. All right. Finally, let us conclude class with the easiest and most relaxing kind of example, the distinct real root case. How about x squared y prime prime plus 3 x y prime. You guys. There's a very important, this is not a nice problem. It is missing a very important thing, x. We just found the solution with the x there. Without that x there, it's a much worse problem, as we'll explain eventually. So that's I don't know. I have trouble seeing this in my head. I guess that should do it, right? Plus y? Plus y is nice. All right. It's on you if it doesn't work out. It's here. So r times r minus 1 plus 3r plus 1 equal to 0 is my characteristic equation, which is r squared plus, hey, no. I don't want it. You monster. That makes it repeated. Which is what we don't want. Here, if we just get rid of that, it's good. It's not great, but it's good. So this is r squared plus 2r equals to 0, which is r times r plus 2 equals to 0. So we get r equals to 0, and r is equal to minus 2. So guys, when I took differential equations, you know where I saw this the first time? So there's the general solution. This is very much like what we already did. It's just the difference is the characteristic equation. It's not just directly the same pattern as the differential equation. You have to do this r times r minus 1 for the second and just r for the first. And if you have a third order problem, you'd have r times r minus 1 times r minus 2. And then the second derivative would be r times r minus 1. The first derivative would be r. You know, I showed you what happens in general, but I don't usually have much patience for doing higher order problems, too many higher order problems here. But here's the thing. For me, when I took differential equations, the first place I saw this problem was on the final. So like the professor didn't talk about the Cauchy Euler problem in the course of the regular part of the course. On the final exam, he states, you know, like the generic Cauchy Euler problem, and he says, suppose x to the r is a solution, what condition do you need on r? That was actually a problem on my final. And the engineers were not happy with it. Yeah, I think so. Because they weren't happy with it because it just required them, I mean, it wasn't a problem they'd already worked, right? It was just, you just got to like think about it, you know? But it's not that hard. You can just plug it in and work it out. It's pretty much the same thing. So we can also do variation of parameters, right? If you, instead of having 0, you put g over here, we could do variation of parameters problems with these just like we did for the constant coefficient case because we have a way to find the fundamental solution.